Hello and welcome to another one of these ADD videos. We're going to look at the graphs of enzyme kinetics. You've already seen, I hope, in the initial video of enzyme kinetics, the basics, the saturation curve that's exhibited when you plot velocity versus the concentration of substrate. The initial part of the graph is linear, but as the enzyme becomes tied up with the substrate, it starts to taper off and asymptotically approach a Vmax value. Okay. It is hyperbolic in nature and will change into a sigmoidal curve in the presence of cooperativity. It'll look something like this. So it's a sign of cooperativity. Do that whole video, cooperativity by itself. The next type of plot we're going to look at is a rearrangement of the Michaelis-Menten equation. And this is a Lineweaver-Burke plot. Did I label that last one? No, I did not. Let's label this last one. This is a saturation curve of. And then we're going to look at the Lineweaver-Burke plot. Oops, Lineweaver's one name, isn't it? This is what happens when you make videos at 2 a.m. And it's actually called a double reciprocal plot. It's a formal name, but most people just refer to it as a Lineweaver-Burke, and you know that it's double reciprocal. And as the name implies, the axes are both going to be reciprocals. So here on the x-axis we're going to have 1 over velocity, and here on the y-axis we're going to have 1 over, wow, I really am tired. The y-axis is 1 over velocity, the x-axis is 1 over substrate concentration. And what happens whenever you do this is you end up with a straight line as opposed to having to guess what the asymptote is. And it allows you to extrapolate down to the x-axis. What is the benefit of doing this? Well, you're able to then use the fact that the x-intercept right here has a relationship. The x-intercept for a Lineweaver-Burke plot is going to be equal to negative 1 over km. The y-intercept of the Lineweaver-Burke plot is going to be 1 over Vmax. And then the slope, this line, is going to be equal to Km over Vmax. Alright, that's quite a bit of information that we get there. Now, there's also the Haynes-Wolff plot, and the benefit of the Haynes-Wolff plot is that it doesn't overemphasize the data that you get at the low concentrations. Sometimes the Lineweaver-Burke plot is faulty in that sense. So Haynes-Wolff plot, we're going to do the y-axis is going to be substrate concentration over the velocity of the reaction, and we're going to have the same x-axis. as your saturation curve. Alright, and if we do that one, when we get the linear relationship and extrapolate down to the x-axis, what we get there is a negative km for the x-intercept. That's where it touches the x-axis. And the y-intercept, as a result, becomes km over v max. Okay. So, why might this be beneficial? Well, you will see when I discuss the different types of inhibition on those videos that each inhibitor has its own characteristic Lineweaver-Burke plot. For instance, if I were to give you the example of here, and let's say I added some amount of inhibitor, got that line there with this x-intercept, and then added some other amount of inhibitor, twice the amount I initially added, and got that one. Well, that right there, because they're all going through the same y-intercept, would be indicative of a competitive inhibition. This is a mode of inhibition that will have its own video dedicated to it, but just kind of showing you what you might use a Lineweaver-Burke plot for. So if you're given data, you could take the reciprocal of your velocity and of your substrate concentration, and then plot them. And do the same with the inhibitor concentrations. You will have new rates at those inhibitor concentrations and plot those. And then see the behavior. Some might have the same y-intercept like we do here. Others might have the same x-intercept, and those would be characteristic of a different mode of inhibition. Okay, but inhibition is not the topic here. It was the graphs, and I have covered that. So make sure you know the differences between a saturation curve, Lineweaver-Burke plot, and Haynes-Wolff plot. Okay. Again, the advantage of the Haynes-Wolff plot was not overemphasizing data at low substrate concentrations, because that is a flaw of Lineweaver-Burke plot. But for our purposes, we will use Lineweaver-Burke plot when we're doing our problems to determine the types of inhibition and things like that. I hope I've clarified any confusion you might have over the basic plots.